In the YouTube.
You know, yeah, exactly. Now we're live. And then the other one is just, I just want to start it directly. There you go. And I mute myself there. Okay, great. Okay, perfect. So let me share the screen again. Share. Can you guys see the presentation?
Yeah, but it's not in presentation mode. It's still in.
Right. So now it's in presentation mode.
Perfect.
So thank you, everybody, once again for coming. As I said, look, 100 of you that's already there that are here for our online SPICE-SPIN+X seminar series. For those of you who were last week, I forgot. So I thought it was SPIN+X was this week. I forgot it was the 1 week after. Thank you for showing up. Just a reminder, next week, unfortunately, because of commitments that we have, we are not able to have the seminar, the online seminar. And then the next seminar will be Marco Gast from KIT, Karlsruhe Institute of Technology, that will give a talk. As usual, we are organizing here from a Spin Phenomenon Interdisciplinary Center that I co-organize with Cairo University, which is now in Duisburg University. And together with the SPIN+X Collaborative Research Center, led by Martin Schliemann and Burkhard Hillebrands in Kaiserslautern and Matthias Chloe in Mainz. Today's speaker, it's a pleasure to introduce, is Stefano Bonetti. He is an associate professor in Stockholm University, as well as a professor in University of Venice. He's in the process of moving to Venice more permanently. But he had it a large part of his career, or I guess, from here in Sweden, and this is where. But he's been one of the leaders in the laser field, and a strong laser field interaction, near infrared and terahertz range, in multiple quantum systems, ultrafast dynamics and timescales, looking now also in magnetic systems and phonon dynamics as well. He received an award. He has many awards actually, but one of the recent ones is the Allenberg Academy Fellow in the National Science by the Sweden's Royal Academy of Science, which, you know, the Royal Academy has another award, but maybe that's for later. Yeah. But it's also a pleasure to have him here because we're confabulating and organizing something in Venice next year in September. A beautiful conference that we will advertise it later on, and I hope that many of you show up there. So I will stop sharing here now, and I will ask you, please, Stefano, to please go ahead and I will mute myself as well. Yeah. And
I like the confabulating word.
Yeah.
Okay, so I go.
Go ahead.
So thanks, Jairo, for the nice introduction, and thanks for all of you for coming and listen to this talk, which is. The title is Inertial Spin Dynamics in Ferromagnets. And this is actually a picture that was taken, so as Jairo said, I'm in between places. And this was our kickoff meeting, January 2020, just before the hell broke loose. Probably COVID was around there and we didn't know. But so the group has been changed, but I mean, this is the some of the people that were involved in the work that I will present. Before I present, and since Venice was mentioned, I will say it again. So there will be next year, more or less 1 year from now, the second edition. Now, since the second is going to be a series of a conference, it's called Trends in Magnetism, which was started a few weeks ago by Giovanni Finocchio from University of Messina. In that case, the conference was in Cefalù, in Sicily, close to Palermo. It was a very nice conference, extremely well organized. For many of us, was the first in-presence conference after a long time with the hybrid conferences. And so this is the next. So this is, it cannot be worse. And I think the city is already offering like a good scene where to do it. It's a bit new to a science of this type in Venice. So as Jairo said, I hope many of you will participate. All right, so the talk today, it's about, we start from something that I guess most of this audience know. Maybe there is someone in the field, some new young people or someone switching, so I will just introduce it briefly. But it's the Landau-Lipschitz-Gilbert equation, or LLG. This is actually this is what kind of the topic, or beyond the LLG equation was the topic of another SPICE seminar not too long ago, given by Professor Ulrich Novak here at the SPICE seminar. And the reason why this is so important, this equation is so important, because it's basically is the equation that describes the way magnetization moves. Okay, and this is a relatively simple equation. It basically tells the dynamic of the magnetization is described by two terms. The first one, which looks like this, M cross H, effective. Now we'll tell you what that is basically describes the precession, the Larmor precession of the magnetization around an effective field. The effective magnetic field can include the Zeeman field, the crystalline fields, the anisotropy terms, anything you can put there. You will have a torque on the magnetization. If they're not collinear, the precession will start. So this would go on forever if it wasn't for the second term, which is called the Gilbert term. So the first two were given by Landau-Lifshitz, and then Gilbert formulated the way to include damping in the proper way. Landau-Lifshitz also did it, but this is the way it's now currently accepted, is to basically tells you that at some point the magnetization will align with the effective field. So if they're originally misaligned, they will align. The way they do it, if you combine these two terms, is basically you will obtain what you call a damped precession. Okay, and this is how it looks like schematically. Why is this so important? Well, if you watch movies on Netflix, or if you do any data-intensive use of the computer in your daily life, the way the information was put into those magnetic servers where there are magnetic hard drives, it was basically to write the information with the, according to the LLG equation. So basically here, what I picture here is a magnetization switching. So the magnetization going from the north to the south pole, and the trajectory described by this equation with the magnetic torque, and then the precession spiraling down towards the opposite pole that was interested. So in the north, you could think as a digital 1, and the south a digital 0. So this is very important also for our daily life, and this worked beautifully for 50 years or so of magnetic technology. However, there is a small problem. It is wrong. The equation is physically wrong. And this is, of course, provocative. How can we be wrong if we use it for 50 years and actually in devices? Well, the way it's wrong, it is wrong from a fundamental physical point of view, in the sense that it assumes an unphysical inertial tensor. This actually was already known by Gilbert. There are a lot of Gilbert in magnetism, but this is the same Gilbert in the equation, which in a review paper in 2004, there is a nice footnote. It's IEEE Transactional Magnetics, I believe. It said, I was unable to conceive of a physical object with an inertial tensor of this kind. But this somehow, even though it was known, it was kind of put away to not to disturb too much what was working. What is the problem? So if you take a generic inertial tensor, diagonal with non-zero diagonal elements, well, this is the most general inertial tensor that would be okay. But the assumption of Gilbert and everyone that used the LG equation is basically to put two of these diagonal elements to 0. So basically all the tensor is 0 except one element. This is very hard. There is, so as far as I know, no classical objects with this inertial tensor. The closest you can get is a stick rotating around its axis or at its vertex, which has all but two non-zero elements. So but then the natural question is, how can it be wrong if you use it every day? Well, the answer is that this is something that happens quite often in physics. It could be that in the limit we use it, it's correct. So it could be that it's fundamentally wrong, but if we take the correct energy scales, so if the degrees of freedom are separated by orders of magnitude, then it doesn't matter. Then it could be that in the regime we are, then the LLG is okay. So what was done, if you do the correct derivation, this is if you're interested in this topic, I think this article of Jeanette Baker and Chorney is extremely nicely written. It's very pedagogical. It only requires basically physics 101 to be understood. And it basically takes the magnetization as a stick of length m, and it basically calculates the equation of motion. If you do this, I will, of course, for time, I cannot do the full derivation here, but basically you can write the equation for the angular velocity vector, which is this omega, and you would get something that looks like this in a classical rotating stick. And if you include the angular momentum, then you will get this equation. Okay, and then you could take this solve the Lagrangian, you include the Rayleigh distributive function. I found it very, I like this quite a lot when I was a student, this type of mechanics. And it's nice to see that it works. It's complex, so it takes quite some algebraic effort, but it's very clear. And what happens, what Gilbert and others did, I'm just checking the time, so is the fact that, how did they solve it? Well, the approximation was to basically remove the first term. So to put this I1 to 0. And if you see here, if you remove this, then you recognize maybe something that is familiar to you, that you get this proportionality between the magnetic angular momentum and the mechanical angular momentum. So this gamma L, so M, and the proportionality is gamma, the gyromagnetic ratio. But this is a pretty rough approximation. So what if we don't do this? So what if we do it, if we try to do the things without losing that part? This is what they did in this paper. And what it comes out is actually, it's a bit more algebraically complicated, but it's surprising thing, it's nothing, you don't need any crazy assumptions, any difficult mathematics to get there. You retrieve, of course, something very similar to the energy equation, but there is an extra term that pops out. And that's that is proportional to the second derivative of the magnetization. And what does this mean? Well, if the first two were the damped precession, when you put this term in, you actually get nutation. So you get what you would expect, and what we all know it happens when you have a classical spinning top, that you have precession, but you also have the swinging around this precession. And this is called the nutation. Okay, and this tells you something, but here you see, okay, this is, it was a missing part. But if you now identify this new factor in front of the second derivative, is the angular momentum relaxation time, you can also get maybe an intuition why this is not relevant in normal energy. This swing in this notation is actually damped pretty fast. Or, well, let's put it this way, if it's damped pretty fast, then it doesn't matter. Because as soon as the notation is damped, then you recover. If you see at the end of the trajectory here, you don't see any difference between the standard energy and the inertial energy. So it could be that the notation has always been there, but since we never cared with such fast processes, and we never looked there, then maybe the simple reason why we don't see it. But fundamentally, it should be there. Okay, so now before moving forward, it sounds like a pedantic thing, but this is a seminar with a lot of people watching, and also being recorded. I think it's good also to do a bit of cleanup, because it's a new things coming up. And so if you see the equation that was written here, it was the alpha, the Gilbert damping, was factored out of the parentheses, which is mathematically equivalent, but I think it's accepted. And I have to thank, I think, the groups of Oppener and Ulrich Novak to actually try. They also state in the paper, this is a better way to write it, not because it's any difference mathematically, but because if you factor out the alpha, it will suggest that the notation is a dissipative effect by itself. No, the dissipative part is in the Gilbert damping. So in this way, the two are separated, and you don't do the automatic intuitive interpretation of the notation being related to the Gilbert damping directly. Okay, so this is just way. So in the following, I will use these three terms in the way it was written, but historically it followed this way. Okay, so if you go in frequency domain, if you look at the susceptibility, when you include the inertial terms, you would expect then, this was originally done, sorry, I forgot the reference, but this is still a work by Jean-Éric Vegro. And you would expect, besides the resonant at the FMR frequency, you would also expect a notation peak. And here, the position in frequency, so this was the guess, so that it had to be at higher frequency. Because if it would have been at lower frequency, we would have seen it. So we can measure slower stuff, but it could be that we wouldn't have seen it if it would have been faster. But where exactly was a kind of a matter of dispute, because not having seen it is like, where really, how can we figure that out? I can only see that likely it's because of the response function is likely a tiny effect compared to the FMR. So it's difficult, probably difficult to say. Okay, so the story goes that I was actually in Kaiserslautern in 2017 at the Ultrafast Magnetism conference, and I heard Jean-Éric Vegro presenting this, and I was really in awe because I did my PhD also in this equation. I had no idea about this. Luckily, his work was after I finished my PhD, so I could feel like I didn't miss anything important at the time. And what's surprising, besides how beautiful is this idea, was the fact that actually a few years before, I had found in the lab, when I was a postdoc, some weird oscillations at the frequency which has nothing to do with FMR. And when we were starting to play with terahertz fields and ferromagnets, this was really the early days. So we didn't know a lot of things that we know now. And so, you know, there are a lot of things that we didn't understand. So let's try to do the simple stuff. So I put it in the drawer and almost forgotten about it until I heard the talk. And then the idea was also combined to another thing, that I was one of the early users at the facility called TELBE, which is a free electron laser facility which generates terahertz radiation of tunable frequencies. That seems like the right time in the terahertz range, the right time to try to do a so-called a force-associated experiment. So basically do the FMR experiment, but at terahertz frequency. So go around this peak and sweep the frequency and see if we see a resonant response. And I want to remember, this was the last conference I met Jean-Yves Bigot, and it was he was overreading the conversation between me. We were there with him, with Jean-Eric, and I remember he said, "Yeah, you should go and do it with terahertz. That's the right thing." And he actually had the right intuition even then. So he thought in the correct way that this is the way we had to do it. So just to tell you, we didn't know if the notation was to spec at 0.1 terahertz or 100 terahertz. That was the range. Okay, so we went to TELBE, which is extremely nice facility outside Dresden. And basically what you have there is a relativistic electron beam, which is created with a linear accelerator, which is passed into a series of magnets, which if they are in the right, if the electrons have the right energy, the magnets have the right spacing magnetic fields, will generate terahertz radiation, as you see in the middle panel. Then you disregard the electrons and you take your terahertz radiation up to the laser lab, to the terahertz lab, where you can combine it with other lasers to do pump probe experiments. And so this is an example of the type of radiation you can get out of that machine. And then the idea was, okay, we have this that we can do now. We can explore a frequency range which wasn't explored before, where we have an indication something could be there. Let's go and try. So this is a bit more in detail what we did. So it is the setup. So basically it shows the terahertz pulse coming from downstairs, the image I showed before. It gets collimated and focused on the sample. And then we have a near-infrared laser, which is synchronized with the terahertz. And you can do this so-called pump probe experiment. The cool thing here is that terahertz being slow compared to the 50 femtosecond pulse laser. This is basically a phase-stable measurement. So we can really sample the phase of the terahertz radiation. So this is not an absorption measurement. It's a coherent response measurement. And we can tune the time of arrival of the femtosecond laser with a mechanical delay line. So if you change the path, basically, the relative time of arrival of terahertz pump and near-infrared probe is different. So if we zoom into the sample, this is the way we did the experiment and the way we try to prove this, the presence of nutation. It was to basically get the terahertz polarization H terahertz orthogonal to the magnetization. And the magnetization you set with a static magnetic field that you can apply outside. So you have M and H, which are orthogonal. This maximizes the cross product, M cross H terahertz. And this will cause a torque, which will let the magnetization lift out of the plane. And this is the way with the laser, the probe laser in orange here. We probe the polar magneto-optical Kerr effect. So basically we measure the rotation of the polarization of light, which is proportional to how much M magnetization is out of the plane. These are details, but it's important to do this correctly. And to do a first test, then indeed, so we were exciting the magnetization the way we wanted, so that it was a torque experiment, trying to really drive the LLG in with a terahertz coherent field. So we performed the experiment with M and H terahertz orthogonal to each other. And what we saw here, what I plot here, is the MOC, so magneto-optical Kerr effect, so the response, if you want proportional to magnetization, out of plane, as a function of time. And you see the oscillations in the terahertz range. So there's a few oscillations in 10 picoseconds or so. If you, very easily what we could do, we could rotate the polarization of the terahertz beam and put them parallel. And nicely, so it's likely that what we want to do, there is no response. So this is a genuine magnetic effect. So if you, and it's triggered by a coherent M cross H term. Okay, so this is, we tested and we know that we could now do the experiment and try this nutation to test this nutation hypothesis. So if we want to do a forced Lorentz oscillator experiment, this is something again that I like in its simplicity, something that we do in the experimental physics courses with our undergraduate students. And we usually do it with a cart or with a spring or something mechanical. But what you have to remember, which it's important here, is that you expect a larger amplitude of the response when you are in resonance. This is the things that I would say hopefully every student remember even when they leave the university. The other thing that you can look at and to check whether this is a forced resonance response is to look at a phase. Because if you are before resonance, you expect no phase shift, so you expect the driving force and your system to be in phase. At resonance, you have a 90-degree phase shift, and after the resonance, you go 180 degrees of resonance, or sorry, phase shift. And so this is something that likely, because of what I told you, is that we do a phase stable experiment. We can try both. So there will be kind of two independent tests to make sure that actually if we see a resonance, that's actually a resonance. And so that's the first thing I show you is the amplitude response. I pick a few frequencies. I will show you a few more after. And what you see here is, again, the MOC. It says normalized MOC. You have to be very careful in normalized. In the paper in the supplementary material, we explain this. And the reason is very simply because in the response function, you're on a slope. So if you don't take care of that slope and all the normalization or the intensity flux, you can get fooled by where the peak is. But if you do this and you do this properly, you actually, when we look at the trace, we started plotting, we got very excited, of course, because we saw that somehow there seems to be kind of some response at 0.4 terahertz, which increased in test at 0.6, and then decreased again at 0.8 terahertz. So that was very exciting. And I said, we had, but this is just, one of the information we could get. The other is actually to go and look at the phase. And the phase response shows something as interesting, or even that's actually made us extremely excited when we saw this. Because if you look, when this is the magenta line, the red line is the same as I plotted before. But now I zoom in to try to identify the phase response. The beautiful thing with this experiment is that this gray line is not a simulation. This is the measured data. This is the measured terahertz field that we can measure with an independent measurement. So we measure our magnetic sample, then we change the sample, and we measure we can basically characterize the profile of the electromagnetic field. And what you can see, that was exactly what we said before, that at 0.4 terahertz, before this peak in amplitude we saw, basically within the noise, of course, the measurements, the driving force in gray and the response to the system are in phase. They go about 90 degrees out of phase at 0.6 terahertz, and then they're 180 degrees of phase at 0.8 terahertz. So this was kind of say, yes, this is a resonance that we're seeing here. So we put this all together for 3 samples. We try to explore different samples to try to see whether this was consistent, and it seemed that we found. And we could see, so in the left, you see what the experiment showed. This is extremely time-consuming experiment. I think each data point you see there, I don't want to say I forgot, but I think each of them is 8 hours acquisition with unique machine in the world of this. So it really took a lot of time. We did it like 3 times with 6 months apart. So first time 6 months and then 6 months, and we switched the frequency. So we tried to pump, not having any trend to make sure, but this was very robust. And so there is a frequency that is unexpected because it's at 2 to 3 orders of magnitude higher frequency than what the known ferromagnetic resonance in ferromagnets. This seems also to be a slight shift of the peak frequency between different materials. It's in the experiment is very broad, but it seems there, and it's there in the simulation. And we can reproduce nicely with the inertial LG equation the peak frequency and the phase shift. That is immediate. So as soon as we put the parameters there, it reproduces what we see. But we don't have a good the line width is not reduced. As you see, the simulation underestimates by quite a lot. Actually, it's almost an order of magnitude the line. But so this is actually one of the point of disputes with the referee. But I think we were very open. We tried also to include temperature, include micromagnetic simulations. We couldn't get it out. So luckily we were able to convince the editor that even though there is something unexplained, if we put it out in the open, I think this was worthwhile getting published. And so we got this. But of course, it's like it's not satisfying when you have such a big discrepancy in your data and in your explanation. So there were a few opinions actually, and this is one of them. So first, so it's nice to do this force oscillation experiment, but it would be even, I wouldn't say it would be even nicer. I would say it's necessary to also see whether you can actually get the free nutation oscillations. It would be nice if we could trigger your system and then see it swing without you driving it with a strong field on top, and then infer what was below the field. So that's one of the idea. As I said, the damping seems to be too large. So when I say too large, what we did is that we characterized those samples with standard FMR spectroscopy, and we extracted alpha, the Gilbert damping, and then we put it in. So this was an independent measurement to give us a parameter we use in the simulation. So we didn't fudge any numbers there. And that was an assumption. So maybe there is something wrong in using that Gilbert damping measure at a few gigahertz instead of a terahertz. And also it seems relatively weak. Well, you could debate whether 20% is a weak effect or not, but it seems to be that, well, with this broad signal, it's the change in the material didn't change much in nutation frequency. So we wanted to know more. So what we did is that we tried to get some intuition and some also, so we started to get excited about these works. We read more and said, like, what can we do? So microscopically, there is a way to actually find the inertial effects automatically if you include higher order spin orbit terms, those proportional to 1 over c to the 4th power in the Dirac Hamiltonian. I will discuss this a bit later and mention the work that actually did this more systematically. And the first idea, so very naive, but you have to try something in this direction, is to try to measure materials where we could control, and also idea right here, but with relatively strong magnetocrystalline anisotropy. So actually those materials we looked, they didn't have particularly strong magnetocrystalline anisotropy. So can we actually, since spin orbit and magnetocrystalline anisotropy are related to each other, can we, try this material and see if this affects somehow the nutation frequency? The second idea was related both to the line width and furthermore to the to see the free oscillations. Instead of using this Telbe facility, which has this what we call it monochromatic, but a narrow bandwidth field, can we use a tabletop single cycle broadband field? So we basically hit the system impulsively and then see if we see a swinging after the system relaxes by itself. And this is something that we were building in my lab. I mean, it was there, but it's a lot of details. I would not bother you, but you really need to get to this state-of-the-art megawatt per centimeter fields to have enough power spectral density to drive these notations. And I will show this in a moment. Okay, and which sample do we look at? So one thing that we had recently published, so we started working, of course, before. There's also another discussion that was born out of this meeting in Kaiserslautern in 2017. So it's a very prolific conference at the time. I was talking to Eric Fullerton, and I was arguing with him that, I mean, I think there should be a way to see something. So it would be very surprising if you have a strong anisotropy in a ferromagnet that you would see no difference in the ultrafast demagnetization. So he made us this extremely nice HCP epitaxial cobalt films that we pump with near-infrared laser pulses. And what we saw, this was a very careful measurement. We reproduced this, we put all the statistics also in the supplementary material of this work. It's actually that systematically, the hard magnetization axis relaxed faster than the easy magnetization axis. So, and we could see that this anisotropy was found at, this is not seen in this picture, but it was seen at the ultra-fast under femtosecond magnetization timescales, at this fast recovery, and also in the Gilbert damping. So it's at all timescales. And so this is still not done with terahertz, it's nothing to do with notations, but we had a system where the magnetic crystalline anisotropy is so strong it actually affects even a highly non-equilibrium say, experiment as the near-infrared pump experiment. So we said, let's try to use the same systems. For technical reasons, in the Terra setup, we could not do this rotate the sample like we do in the near-infrared pulse, just because we didn't have enough field. There's some space constraints. So we decided to compare 3 cobalt films with different epitaxis, with different structure. So, but the experiment is similar to the one I showed before. Now the pulse looks like this second derivative of Gaussian. That's the way you can see it. Basically, the single cycle pulse. This integrates to 0. This is a single cycle terahertz pulse, which is a bandwidth which is in the within 2 terahertz. It's about 2 terahertz bandwidth around here, center about 1.5 or a bit more terahertz. And then we probe again with MOC. And what we did is compare epitaxial FCC, BCC, and HCP cobalt films. And so from a static characterization, you can see that the 2 cubic structure, which are the FCC and BCC, they're actually quite similar in anisotropic energy. So if you take the loop, they're similar. But the HCP, and I will show this also later, has a much larger coercivity along the easy axis. And also, if you go along the hard axis, actually the cubic system actually don't have almost any anisotropy in the plane, and while the HCP has a huge anisotropy. So those were 3 films with remarkably different magnetic crystalline anisotropy. And so we did the experiment, and so what I show here now, this is, you will see now the Kerr, this is called delta theta Kerr, is simply the magnetic optical Kerr effect, is the variation of the rotation depolarization as a function of time. And this is the dashed line here is what the LLG without inertial terms would expect you to see. So a response which follows the shape of the terahertz single cycle pump. So if you do this, we do this on the FCC film, we see that actually the qualitative shape is there. Forget about the amplitude. This is not, there are a lot of normalizing factor with absolute amplitude here between films. But basically, it looks pretty good, except that the response is shifted in time. This is very important, and I'll come back to this later. If you do this with BCC, it almost looks like identical. I mean, slightly different amplitude, but if you scale it, it's the same. It's a very similar response to the FCC. If you do the HCP, it actually looks quite different. Besides, the amplitude also looks like even more shifted in time. And this is basically the maximum shift you can get from the peak of the LLG prediction and the peak of the film with the largest shift. That's about 400 femtoseconds, which we can measure very reliably. So we reproduce this, and you can do this many times. And with the other 2 films, something between like 200 femto. Okay, so, and the biggest surprise was also when we came in and we zoomed on the trace that looks like noise. Actually, we saw that there were terahertz oscillation hidden there. And this is, again, I don't want to bother with details, but here we are at the microradians level. So the rotation here is very tiny. So it took us quite a lot of time for the setup to be so sensitive to actually to see this. But you really need to have, I think we are in the 10 to the minus 5, 10 to the minus 6 a noise level in order to see this. So you need to have a setup that is able to see really small deviation of the magnetization. And that was very exciting. And because could it these are those the free nutation oscillations. And so we went on and checking. So we do all the checks you can do to try to see, to change things and see if they change in a way that you would expect with the inertial energy equations. Not. This shows the response. This is in this case for the FCC samples for different terahertz pump magnetic field. So 0.3 Tesla is the maximum we can have. And given that, the noise is, we were very close to the noise, so we did 1/2 and 3/4 of the max value, basically. And nicely, so you see the oscillations, and you see that they, in this regime, they increase, so the amplitude oscillation increased linearly with the strength of the terahertz magnetic field. Another things you can do, again, that's how we did in the Intel base, like you control the polarization of the terahertz pump. And again, very nicely, if you do the M cross H experiment, you see the first is the coherent precession. This is really the off-resonant response of the magnetization to the single cycle pulse. And then the swinging. If you put M and H parallel, you see what we also know this. We did some work on this is a demagnetization. So it's simply the energy that put in the system demagnetized, but no oscillations, no notations, no coherent response. This is very, again, it's understandable in the framework of a coherent dynamics with the magnetic field. And so if you do the FFT, then you see what you expect to see, and also something more. That was really surprising, that we see the peaks at 1.3, 1.4, and 2.1 terahertz. Of course, this is simply the FFT of the signal. And in the light color is the simulation of an inertial LG. So we could do this. So it goes there, we can reproduce it. But also some weird peaks, of course, very noisy, but I mean, they are pretty close to being the harmonics of the precession. So this was something that we couldn't let go. And the other thing is that if you do the simulations with the inertial LG, we reproduce the nutation frequency, the line width, that this time we don't assume from the Gilbert damping, so we measure it experimentally. So now the line width is taken from the actual experiment. And also the temporal shift of the inertial response. This is, in a way, I think this is a nice way to see this as intuitively as thinking as inertia, something that basically makes your system heavier to move. So if you have a non-inertial system, it will respond immediately. If there is inertia, so it will take some time before it starts. And this is what the inertial LG includes. And as I said, the nice thing is that we only have the input parameters is basically what we see already. So this time the inertial LG is measured based on the damping and on the frequency that we observe. There is no extra information we put in. But we don't see the higher order harmonics. So these are new things that we don't reproduce with inertial LG in its current form. Okay, so, and I can tell you, this is something that I think it's most of it is reproduced by the inertial LG. So we stopped here in the sense in the analysis. And there are ideas how these harmonics can go in. But I think before doing that, I think I want to analyze a bit more the details of the microscopics of what we see. Because the second very nice paper, which I recommend to read, if you're interested in this topic, is this paper from the group of Peter Oppenen, where they derive, starting from the Dirac-Konsham Hamiltonian, what should happen if you really do start from fundamental quantum mechanical equation? Does inertia, does nutation come out of this? And the answer is yes. If you do this, I have to say, I'm not a theoretician, but and I didn't understand all the passages of the paper, but it's extremely nice written. So I enjoyed reading. I give it for granted some of the passages, but it's really, really nice. And it also gives a nice historical perspective of this, all this inertia business came about. And so if you do it, it gets quite some algebra. You can write a spin Hamiltonian, which has a lot of terms. I mean, this is just to show how complex it can get. But I think what is interesting for me is that there is the last terms as the second derivative in time of B, where the magnetization is in. So you actually get the second derivative of B. This is for the single particle. In the paper, they also go ahead and actually do this for a magnetization for the case of a sample with a certain volume where there is a uniform magnetization state. And what you can see is that actually you recover the equation that was given in the beginning. So from very first principle, you get these three terms with the Larmor precession, the Gilbert damping, and the new inertial term. They also give expression for the Gilbert damping. I will not go into details. So those are tensors. So it's quite, I guess, complicated to calculate them to first principles. And they also give it for the inertial damping. But what is nice is that from this formulation actually comes out that these terms depend on Chi-m, so the inverse of Chi-m, which is the response function of the material, which of course will include. This is the way the variation of m with the applied field, which will include indirectly or in some way the magnetic crystalline absorption. So in a way, the intuition, so that this could actually happen, and this gives us a way to actually model this more fundamentally. So we didn't do this in the paper that is now in archive and under review, but what they also suggest in the paper, we did it, at least was a bit easier to do, is that if you see here, the both terms have this dependence on Chi-m. And in the right limits, you could assume that the ratio of these terms I mean, this material-dependent variable parameter would disappear. And indeed, if you take our 3 samples, you take the ratio of the I, which I called eta before, the terms in front of the second derivative, alpha or gamma here. If you take the ratio, you actually get, well, this number is about 750 femtosecond plus minus 50 femto for all 3 samples. And the error which we estimate the parameter is 10%. So within the error of our measurements, this is basically a constant. So this seems to validate also from a microscopic point of view, this approach. And the nice thing is that if this is true, and if this number could be calculated in some way, you really need, I mean, basically there is only one free parameter, which you can still get from experiment, but once you know the nutation frequency, you know the damping or vice versa. So, and this is kind of reducing the degrees of freedom. I think it's a nice, or the free parameters is a nice signature of something that start to get a coherence in itself, also from a microscopic point of view. So this is the, I would say we were very excited when we also get this to actually work out. I think the experimental evidence is enough, I think, to convince that there is something else we don't understand, that the inertial LLG is able to reproduce nicely. But I think this is also gives it a twist that has, I mean, we can also try look forward and in either direction now that we have such a strong basis behind. And just to show you, so again, this it was not meant to do it quantitatively, but I want to stress that this, if you solve this, it would show you that if you solve the equation I showed before, it would tell you that if the strength of the anisotropy would increase the nutation frequency. You need a few passages to see it through, but basically it's in line with what we saw. So the low anisotropy films, which were also very similar in phase, the crystal structure of BCC and FCC, as I said, is quite similar. They got basically the same nutation frequency, which is 50% lower than the one of the sample with the largest anisotropy. So there seems to be a dependence, which is not likely linear. So I mean, the anisotropy in the HCP sample is several times, it's almost 100 magnitude larger. So it's not really a linear relationship. But it's there. It seems to be in the right trend, as the theory says. So this is another point. Another thing I would like to make, because I think, I mean, when we got these results, and we got, of course, very excited, also very scared. What is if everything is wrong, or like there is something that doesn't work? So I think we did on purpose actually to try to use samples that were grown by different growers. And this is, for example, I mean, the two of the sample, the FCC and HCP. Sorry, I forgot the label, but blue FCC, green HCP are grown in San Diego, and the orange one is in Milano. But so this shows that it's not, and they all have different capping layers. So you really need, we try to say that to exclude anything that could be like a constant in your measurement, you sometimes do not expect, that could actually, give you a false positive, let's put it this way. And I think in general, another message I think is important for ultrafast magnetism. I think going back to model systems that were not studied as much, and I'm guilty of that as well, I think it's something that it's where the theory, we can work together with theorists, with experimentalists and theorists, because they can help us model this stuff. The polycrystalline are nice. You can do a lot of things. You can grow in them also in membranes. I do also a lot of X-ray experiments. So I like this flexibility. But to understand fundamental things, on top of maybe extrinsic causes, I think really we need to put an effort to go more for model system. There is not much done in literature on this. And this is one example of one of the things that probably you would not see in a non-model system, or at least in something where you don't have full control of the anisotropy. And so I'm almost done. So what you could ask yourself more pragmatically, so spin notation into inertia in ferromagnets, when does this matter? And so we have another work under review where we actually try to see how this inertial term will actually affect the switching. So there's this basic process I was telling you before that it's happening, I don't know how many times, I mean, billion or trillion times per second in our data centers. But if you do the switching, you can solve the LG equation, or you can solve the inertial LG equation. That's what we did. And In this work, we look at two cases of switching. We call them one the precessional switching, the other the ballistic switching. Sometimes in literature they're used as synonyms, but in our case they're not. The idea was to show how a terahertz pulse, in this case we simulate as Gaussian, so half cycle, so Gaussian magnetic field pulses, those that you could give with a current pulse, for example. Quite intense and quite short, so not really the state of the art, so maybe it's a bit beyond what is happening, but still interesting. And so you can see here, this is the nutation that you see in the start, and then you see the magnetization spiraling, as I showed before, precessing around and getting to zero. But you also get the ballistic switching if you really with your pulse, which is strong or long enough to actually bring it to basically the other equilibrium position right away. If you do this, then you would see that, well, the nutation actually moves with the trajectory. And this is what, or the inertial terms move a bit the trajectory. And what we look at, we try to simulate the switching time as a function of this that is basically the magnetic field pulse energy. So it's is given in Tesla picoseconds, basically. So it's the area under this Gaussian of the magnetic field. And what you see is that for, let's say, small and magnetic fields where you actually get into the to the precession regime, there is basically no difference between the precession and nutation. This is actually, it's also nice in the sense that it goes back to the world we know if we just have this. And so this is the region where you have the switching time, which is on the 100 to picosecond to nanosecond. However, when you reach the ballistic region, so you see a drop in the switching time. So this is now goes in order 10 picoseconds, slightly less. And you see two things. First, that if you have inertia, it takes a bit more magnetic field energy to get there. And this is again, intuitively okay to understand if you have a massive object, it will take more energy to bring it into another potential well. But once you brought it there, it actually stays for longer. So the width of this region is larger. So in a way, so if this experiment will be realized in the future, if the storage will use actually short and more intense magnetic field pulses, you can actually see this in the switching process. So the inertial terms may become relevant also for the stability of a magnetic bit. And so this is, well, that's what I said. It's basically the inertia broadens the magnetic field range of the ballistic switching when you use coherent torque. So this is important. This does not include the ultra-fast demagnetization effect that you do with femtosecond lasers. So this is something that could be tested. And I think the nice thing in this paper is actually we try to give a nice, an intuitive interpretation in terms of energetics of the process. So yeah, if you're interested, I strongly suggest to read this. Okay, I'm almost done. I'm basically done. So which were the open questions? Where do we want to go? So the question is that, of course, we saw that the nutation damping is much larger than the Gilbert damping in the FMR. But why is that? I mean, is there a way we can understand what is the microscopic damping processes that affects one and the other? There are different timescales, so it's not unexpected that this could happen, but which are those and how can we understand better? So how do we understand the harmonics of the nutation? That's the other thing. There are ideas, I mean, there are suggestions that, and has already been published, to include a higher derivative of the magnetization in the inertia, in the LG equation. You will also get those. Yes, it sounds like, yes, this would make them pop up, but why would you need this? So that's another point. Can we test this magnetocrystalline hypothesis in other materials? Again, other epitaxial system where we could, I mean, now we have 3 points. Can we do it more? And can we control this inertial effect with sample engineering? I think from practical point of view, the question is, I mean, the effects that we saw are rather small, as I said. Can we maybe enhance them with some sample engineering? So just as an interesting fact is the first time I saw this weird oscillation was a sample where we had a platinum cap on top. So, and somehow also platinum is known to somehow do something with the spin orbit coupling in the material. So the question is whether can we do this with interfaces or in engineering or similar approaches to actually enhance these effects, make them more important. So those are a bit of the question that I have. And with this, I thank you for your attention, and of course, thanks to the funding agency that is allowing this. and I have to finish with this again to promote. So what was the word I forgot already? Confabulating.
Confabulate.
Project that we have with Jairo. Thank you. Thank you for it.
Thank you very much. So as usual, please, there's some Q questions. So let me look for who I think I'm going to promote you. So wait, and then go ahead. I think you've just been promoted. Should come to the panel. So everybody that asks the questions will promote to panel. So go ahead and once you're promoted, Wei-Dai Wu, please go ahead and ask your question.
Can you hear me now?
Yeah, we can hear you.
Okay, thanks. Thanks for the very nice talk. I have a maybe very naive question. So, is there a similar inertial term in antiferromagnetic dynamics?
Yes, it's a very good question, and there is a very nice paper published not too long ago by this one. Can you see the one I'm pointing with the slide?
Yeah.
So they actually analyze exactly that. Yes, it's in the terahertz, and the suggestion is that in antiferromagnets this could be actually stronger because the precession notation could talk more easily because they're close in frequency. So the answer is yes. It's a bit tricky. It's actually one of the goals of the conference in Venice would be to actually we want to learn how can we probe antiferromagnets in a better way. So optically, when m is equal to 0, the effects are even smaller. So we need to find some tricks actually to detect those signals. But in principle, yes.
Okay, thanks. So can I ask just follow up?
Yeah, go ahead. Go ahead.
In the frequency range, also in the terahertz.
Say again,
frequency, the nutation frequency for antiferromagnet would it be similar?
Yeah. So I think in this paper they say it should be there. Yes, I forgot exactly where, but it's in that range. Yes.
Okay, wonderful. Thank you very much.
Thank you.
Alexander, go ahead and ask your question, please. Yeah, we can
hear me. Yeah. Hi.
Stefano,
thanks a lot for the talk. So my question is the following. I have two questions, and I'm very interested. Yeah. So first of all, those ringing that you see after the single cycle pulses, right? If it's nutation, how would you explain that it couples into the out of plane magnetization component, right? I mean, you imagine this nutation going around and then this wobbling along the precession, but then it always changes the component which it contributes to. So there should be also some modulation. So it's tricky. I don't understand it.
Yeah, no, I know it's tricky, and I can tell you why it's tricky. But do you want me to answer this, or do you want to ask the second first?
Well, let's do it one by one. I don't know.
Okay, so it's tricky because I think it's maybe again my fault. I mean, the picture we do is exactly what you do, but what is happening is this, and this thing is processing. So we are not making this. So we are really touching the magnetization just a little bit because we are completely off Fresnel. So I think the point is we are in the small precession limit, and we're basically just going up and down.
Yes, but I mean, a single cycle terahertz pulse would move it out of plane and then basically return it back if there is no nutation. And if there is nutation, then it kind of
but it seems down. Okay. So it seems that there is first some. Well, we are not maybe going back exactly. There is some demagnetization. I think it's a good point. I don't have the perfect answer. I think that a lot has to do with some sort of, we're in the small perturbation limit. So we basically trigger impulsively. We are also measuring, I should be honest, in this single cycle, we're measuring 45 degrees. So we both have the polar and longitudinal components, and we cannot disentangle it. So because of technical reasons, so it's a bit of dirtier signal than I want to tell them.
Okay.
But that's what we have to do. But you're right.
You also have longitudinal effect, true.
Yes. So, but you're right. In principle, you could have both. So, ideally, the better experiment would be to maybe do the two pure polar and pure longitudinal. Yes.
Yes. And I just remembered also when reading this paper, those high, several peaks in the frequency, so those harmonics. And if you say it's some kind of nonlinear effect, would it also have nonlinear behavior with respect to the fluence, with respect to the field that you're applying?
Yes.
Then you should see that the peaks go down maybe at lower driving field.
Yeah, so the point is that I also thought this was a nonlinear effects at first, but now that we found that there is this, maybe could be higher derivative terms, I don't know.
Okay.
This is something that, but you're right, it's this. But in this limit, it seems at least the torque seems to be linear. But you're right, it's the this is the open question. I don't have an answer to this. Yes.
Okay, thanks. And
Then-
final question. Sorry for taking too long.
No, that's okay.
This Telby experiment, right? As I understand, you were normalizing by the electro-optical sampling in zinc telluride,
Yes.
like 100 microns thick, if I remember correctly.
Yes.
And this may cause some problems, especially if you have a very narrow band pulses.
Yeah.
If there's an echo coming in at some point, you just won't see it, and this will just modulate your response. So, do you know anything?
Yes. So that's a problem with the modulation. You're completely right. I forgot if it's it's a couple of picosecond or maybe a bit more with 100 micron, or if we're using 300 micron. So it wasn't as close. It was a bit, but that is only a problem in the modulation, not in the magnetization signal, because those were on 0.5 millimeter or more samples. So we saw the echo, but it was farther away, so we didn't see the modulation. So, but you're right that to set the phase, so for the low frequency at Telbe, we had to be careful. So we basically cut it. But once you have 1 or 2 cycles, you can identify your position.
No, but I'm talking about a different thing. I think if you try to measure your electric field using electro-optical sampling, and your driving pulse is, let's say, 0.2 terahertz, there is no way you can see this reflection. It's already inside. This just reduces the amplitude.
No, because it's separate in time, and the first oscillations will not see it. You have an interference after a few cycles. So if your thing is 10 picoseconds and your reflection is 5, the first 5 picoseconds will still only see 1 pulse.
Yeah, but it can be much shorter than 5. That's what I'm saying. It can be 1.
No, but that's what I'm saying. Yeah. But the point is that we had, I think, always at least a couple of cycles where there was not this effect. So we estimated, and I think we use actually the 300 micron. If I'm not, I have to check this. I don't have it on top of my head, but it's a problem if you don't think about it. But you can solve it if you think about it, because you can also simulate it. Because you can simulate this very easily. It's the interference of waves.
Sure. Of course.
Okay, perfect.
Okay,
so let's move on to Massimo and afterwards Gisela. So Massimo, go ahead and ask your question.
Okay, Stefano, thanks a lot for this talk. It was really, as usual, very good. I'm a little bit puzzled. I mean, I should read the paper by the open air group. I was a little bit puzzled by this higher order relativistic term. Normally, if you look for relativistic effect, you have to have something that goes close to the speed of light. So in solids and so on, you look for the core levels of heavy atoms and things like that. But here you're using cobalt 3D levels, the magnetism. These are not so
I'm actually Massimo.
relativistic. Why this shows up in an observable effect?
Actually, Massimo?
Yeah?
I'm actually promoting Peter to panelist so he can answer you.
Good.
So I think he's coming in a second, this Peter.
Okay.
So Peter, if you would like to answer that, go ahead, because it's a theory and to Stefano will be unfair.
Yes.
But Peter,
honestly, I would say that I would not know how to answer.
I didn't want to put Peter on the spot, but I saw him there. So.
But okay, yes, it is a good question. And the point is that we don't know in the paper how big is the this eta that is in front of the term. And so at that point in the paper, it was left open. And of course, it is correct that it should be smaller. I think that in the end, actually, it is consistent with the small, actually the time scale that Stefano found. Okay, so it is possible, but I have to say also that in the paper we distinguish between intrinsic inertia and extrinsic inertia. Okay, so the intrinsic inertia is just the material cobalt, but there can be cases where you have extrinsic inertia, and that is discussed in some other papers, where you have leads and you have damping or dissipation to the leads, and then it can be different. And then actually we do not know what is more important, intrinsic or extrinsic. So still the question is completely right. We do not have a good feeling of the coefficient in front of the inertia. And therefore, I think actually I had not seen Stefano's presentation, but to pin down numbers is very good and is needed in order to actually address precisely the question that you were asking Massimiliano.
Mm-hmm.
Yes.
Okay.
So, and I can tell you that it's also the quantity. So I have to do this estimate properly, but the amplitude notation is between 100 and 1/10 of a degree. So it's really, really tiny. I mean, so I think all this, both the frequency and the amplitude, we should put them in, but they're small. They're really small. So I think maybe, at some point we will be able to do this.
So let's just, so thank you, Massimo.
Thank you, Massimiliano. Massimo, sorry.
Massimiliano, sorry. Gisela, go ahead and please ask your question.
Can you hear me?
Yeah, we can hear you, Gisela.
Yes.
So I have thanks for this very nice talk. I have a question concerning the ultra-fast demagnetization process. You pointed out that this effect depends strongly or is related directly to the anisotropy, the magnetic field anisotropy.
Yeah.
In the ultra-fast magnetization process, the temperature changes as function of time, and with this time, very dramatically the anisotropy. How this can be handled?
You mean, so sorry, it wasn't super easy here. So your question was on the
if you have an ultra-fast demagnetization process and the temperature is changing as function of time, then all the anisotropy changes as function of time. And how can you deal with this?
Yes, so now that's true. So your point is the effect of temperature, right? Yeah. In this. So how we include it? Okay, so there are two things. So with terads, even though we drive pretty hard, the amount of energy we put in is not that large. So temperature is not that much of an issue. So the nice thing of this experiment, really, it is a torque-based experiment. There is some heat, true, but the demagnetization there is less than 1%. So we don't include it. We could include it. I mean, you can include both M and anisotropy will change with temperature. I think you could measure it in some independent way included, but I think in a terads experiment, those are the higher order perturbations. What we saw in the ultrafast, maybe that's what you were referring to, where we demagnetize most. Where is it? Where I have it here, this one. This also was together with Peter. We did ab initio calculation. So, and I would say that at this ultrafast time scale, at least the demagnetization also recovered the temperature is a bad quantity. So, but I think in a full ab initio calculation, so what we could see, even if you forget for a second about the temperature, there was, if you do the full ab initio calculation, including magnetic crystalline anisotropy, there is indeed a different relaxation in that you would expect in ultrafast demagnetization. It's not, well, it's actually quite a lot in terms. It's not much in the experiment, but I think the increased electron-phonon coupling in one direction according to the other, which was the main thing, the main reason, is about 50%. That was the calculation that Peter and his group did. It's a good question. I think temperature will be there and it will make things, disturb things, but I think it's not the main, my answer to you would be, it's not the main effect in a way. It's there and somehow it quickly re-equilibrates to a point that is not that different from the equilibrium.
I have a short question additional. I've looked to your paper and you said the perpendicular standing spin waves will play no role. Have you checked this by looking at samples with different thicknesses?
Yes, so thank you for the question because this is a very good point. So actually the 3 samples that we looked and in this paper, they all have different thicknesses. Oh, sorry, 2 have the same and 2 which have not the same frequencies and so on. The thing is that I think we now have work, I'm just collaborating, and I think we understand this better. But the point, so there are 2 things that do not go well with this. So the first is that the terads is basically uniform in the sample. So the skin depth of terahertz is hundreds of nanometer, and we have 10 nanometer samples. So there is no gradient. To get the standing spin wave, you need a gradient. That's the Melnikov experiment where they injected electrons. They could really trigger, like they could inject it really in the first few atomic layers, and then they could get the higher order spin waves. So this we don't have. The second thing that I think we see, it's indirect. With the standing spin wave, you expect the frequency of the higher harmonics to go as the square. So the frequency goes as n squared. But the higher harmonics that we see actually goes with n. So if it would be a standing wave, the energy will go as the square of the wave vector. In our case, there is no square of the wave vector. So this is another thing that kind of disproves this standing wave suggestion. But I think the main argument is that it's the cross section of a non-uniform excitation. With a uniform pump is very small. So you cannot excite a non-uniform mode with a uniform excitation. That's the main argument.
Okay, thank you.
Thank you.
Thanks, Gisela. So Michael Kitzel, can you please unmute yourself and ask your question? Yeah.
Sure. Thank you very much for your presentation. I was just wondering why the angle between MH loop measurements for the cobalt HCP case was, I guess, 90 degrees, whereas for the others it was 45 degrees.
So again, the phase shift, you mean? Here.
So I think you had some MH loop measurements.
Okay, yeah.
Yes, I was just wondering why it was 90 degrees for the HCP case versus 45 degrees.
I see. Thank you. Sorry, I misunderstood. No, the reason is that in FCC and BCC, the 0 and 90 are equivalent, so there should be two easy axes. So the 45 degrees should be the hard axis in the BCC and FCC, the way we draw it. While in the HCP, the easy and the hard axis are in plane. But so you have basically the C axis of the HCP along the plane, and the hard axis orthogonal to it. Because this is an hexagonal structure. But in the cubic one, the space of the cube are equivalent. So if you want to see on a hard axis, you need to go along the diagonal. But it shows that if there is an anisotropy, it's very small. There is basically no in-plane anisotropy, which I think is one thing that I wanted to say, but I probably didn't. So thank you for the questions, because it made it
no problem.
It made it clear.
So were all the measurements then in plane measurements, or?
The magnetic field was in plane, yes. The geometry of the probing with the light was 45 degrees.
Okay. Yeah. I guess my follow-up question then would be, would one way to, probe the effects of like a Kaplan layer be to have like out-of-plane measurements where you have different Kaplan layers?
Yeah, I mean, sure, absolutely. All this would be interesting. The thing is, one has to come up. I mean, we are improving always, but when you do a terahertz measurement, you're allowed to constrain with space, and it's not easy to do all this. But in principle, yes, I would love to do it. We need to find a way how to do it. You need a very strong magnet out of plane with only basically with projected field, because with a terahertz, you're very close to a sample. You cannot have two poles. You only have one. Because your sample is completely covered by the terahertz optics in front. So we need a strong projected field that has to be a few Tesla. And yeah, I'm looking into buying a superconducting magnet, but it's not cheap and it's not easy to get. So, but in principle, yes, but it's less trivial than other measurements simply because of some technicalities within the terahertz experiments. But that's absolutely in principle is possible, yes.
Excellent. And then the last question from Rolando, please go ahead and ask the question.
Yeah, can you hear me?
Yeah, we can hear you.
Stefano, very nice talk. I was just wondering, nice to see you too. I was wondering what would be different if you were doing this on YIG, for example, on an insulator?
That's a beautiful question. We wanted to do it and we tried. The signal is even smaller, so we could not see much. I mean, we barely saw the coherent response. In principle, it should work only there. One word of caution, though, YIG is a ferrimagnet. It's not a ferromagnet.
Okay.
So that could change things quite a lot. I mean, that would be go towards the anti-ferromagnets, which could be. I can tell you, we tried. The problem was simply like, with thin films with low signal, so we could see barely the precession. So we could not have enough signal to noise to see the notations. And maybe the notation is at another frequency. But in principle, it should work. And I would expect the Gilbert damping be very different. So probably, actually, now that you ask me, probably the inertial frequency could be very different.
Okay.
Yes. That's a good question. I haven't thought about this, but worth trying, yes.
All right, thank you.
Excellent. So thank you. I'm going to end this streaming now. And then
I will put
thank
this
all 150 people, or 50